We're starting section 4.2, and this is maximum and minimum values of a function. We're going to discuss absolute and local extrema, and you want to know what the difference with, for these two terminology is, and then we want to discuss the extreme value theorem and the closed interval method. Closed interval method is how we use extreme value theorem. So local extrema. If function f has a local maximum at c if function at c is bigger than function at x for all x near c, bigger than equal to. And this is the definition we use. That is, f of c is bigger than f of x for all x in some open interval containing c. And if function f has a local minimum at c if f of c is less than or equal to f of x for all x near c. And so the picture speaks the story. And so in here, if you look, you realize that at these few points, here's a local min, here's a local min, here's a local max, here's a local max. These are not the only situation we have local min and local max, so we give you plenty examples of how it works, and we are assuming that a local min and local max does not happen at the endpoint for the purpose of this course. So basically, we either ask for a local max point, or we ask for a local max value, which would be a y value, but local max point is an xy value. So for example, in here, c1 is the x value, c1 and f of c1 is the point, and then f of c1 is the maximum value of the value of the function there, basically. And now, a term extremum, and you hear a lot of times extremum, is shorthanded for maximum or minimum. And so when we're talking about extremum, when you're talking about local extremum at c, then y equal to f of c is a local extremum value, and c and f of c is a local extremum point. An endpoint again is not the endpoint of a domain cannot be a local extremum. It can be an absolute extremum, and we talk about that. And the reason for not being local is because it doesn't contain a neighborhood of points. So a function does not necessarily have to have any local extrema. And so here's an example. Y equal to log base b of x looks like this. The shape that is drawn in there rather than the shape that I drew, and it doesn't have any local extrema. Also, y equal to b to power x is like that too. Neither of them have any local maximum or local minimum. Now look at y equal to the parabola of y equal to half of x2. This one has no local maximum. It does have a local minimum value, which is the y value over here. Both x and y value are 0, so the local minimum value is 0. In here, y equal to 2 minus 0.5x squared has a local max. It has a local max, but it doesn't have a local minimum. It doesn't have it has these two not only have local, and this one has a local min and absolute min, as we discussed. This one has local min and local max and absolute max, but no min or local min. And so local min over here, local max over here, it's obviously happens at point x equal to 0 and it's equal to 2. Now let's discuss absolute maximum and absolute minimum. A function has an absolute maximum at c if f of c is bigger than or equal to f of x for all x, not just the neighborhood, but all x. And a function f has a absolute minimum at c if f of c is less than or equal to f of x for all x. This one, you notice that endpoints can be included in here. For example, in this picture, I can see that these 2 points are local max. One of them is the absolute max because it sits at the highest value y. And so the y value for this point is the absolute max, but y value for this one is not an absolute max. And we don't have any absolute min because these 2 sides go to negative infinities basically. And here is a local min only. Other things to notice if the point, the absolute, the extremum, is not happening at the end point, then absolute extremum is going to be a local extremum as well, but not the other way around. If example 1, absolute extrema. A function can have at most one absolute maximum value, but any number of absolute maximum points. What do we mean? Let's give a few examples of that. First, we start with f of x equal to x squared has no absolute maximum because x to power 2 cannot be arbitrarily, it's going to be arbitrarily large. F of x equal to negative x squared has absolute maximum value 0 at the point 0 and 0, but it does not have an absolute minimum point. Now, another example. F of x equal to cosine of x has absolute maximum value 1, and there are infinitely many absolute maximum points, which is for any k pi and 1 gives you the absolute maximum point. But the value, the y value is always 1 because the maximum points for the maximum value for a cosine is always 1, and that's what we mean over here. There could be infinitely many points, but only one value for the maximum. iClicker question 1. This is section 4.2, iClicker question 1. If f has an absolute minimum value of c, does the function g of x equal to negative of f of x has an absolute maximum value of negative c? And so I suggest pausing and coming up with the answer. So let's think about this function. We're drawing a function and it has an absolute value negative c over here, c, absolute minimum value negative, or I'm sorry, c, and let's say it happens at some point in between, and then so this is y equal to f of x, and then I'll think about another function that is y equal to negative f of x. So the shape of that one looks like this basically. It's the mirror image over x-axis. And so this is y equal to negative f of x. If you compare the two, you realize that this function is going to have a maximum right above there. So this is just to give you an idea of how this works. but to show that this always works, because I don't know if my f of x looks like that. This is just to give me some idea. And to make sure that it's actually always working, remember, if f has an absolute minimum value of c, that means that f of x is bigger than equal to c for all x. Now multiply both sides by a negative sign. You get negative f of x is less than equal to negative c. Remember, if you're multiplying by negative sign, the direction changes. And then notice that negative f of x is just g of x. So g of x is always less than equal to negative c. And that means that g of x has an absolute maximum value of negative c. So this is correct, and it's always. Example 2, local and absolute maxima and minima. Over here, and let's see, where do I see a local maximum? I see one over here because it's sitting above everything else. I see another one over here, sits above everything else around it. See, within a little neighborhood around it, it's the maximum. Here within a neighborhood around it, it's maximum. Actually, this one is a absolute maximum. So absolute maximum at x equal to negative 2 and is 3. And then there is no absolute minimum, because if I look, this point is empty. It would have been an absolute minimum, but it's not going to be an absolute minimum because it's empty. So I can get as small as I want to and get closer and closer to that empty point. So no absolute min. And then local max. Local max, I have one over here, one over there. Do I have any more? Let's see. The definition of local max is that you find a little neighborhood such that for whatever point in there, let's say this is point C over here, and then f of c is bigger than equal to points around it. Our definition establishes that any point over here, not this endpoint or that endpoint, these are not, but anything in between can render a local max. So for any c in -1 and 0, there is a local max value equal to 2. For x equal to -2, local max value equal to 3. For x equal to 2, local max equal to 2. How about local min? Let's move on to the next page and talk about local min. So local min, I see that here is a local min because all the points around it are higher than that. Again, we discussed that this cannot be a local min. It's actually it's not a point, so it's empty. It's not going to be a local min. Over here, it just gets closer and closer to 0. That doesn't count. Over here, can I use any point in here to be a local min? Yes, because the definition says f of x has to be less than equal to f at all the neighboring points, and it's equal to, so it works. So the local min is once over here, once within that open interval. Also, this endpoint is included. That endpoint works as a local min. So the local min happens at x equal to 1, and also for all x in -1, excluding over here. And then for these points, their value is going to be 1. For that point, the value is going to be 0. Now we want to talk about critical numbers and Fermat's theorem. So Fermat, here's the thing. A number C in the domain is called critical number if f prime of C is equal to 0 or f prime does not exist. So two conditions, don't forget this. One is f prime can be 0 or f prime does not exist at C. And so f prime of C equal to 0 or f prime of C does not exist. Fermat's theorem says if f has a local extremum at x equal to C and f prime of C exists, then f prime of C equal to 0. So if this, how it's worded, remember this part. If f has a local extremum, you can also write it that either f prime does not exist or f prime is equal to f prime at C equal to 0. So that's how we can word it differently, because it says if f has a local extremum at C and f prime exists, then it's 0. So if f has a local extremum at C, it's either f prime of C does not exist or f prime is equal to 0. And here are a few of choices that we can have. See, there's a local minimum here, and f prime is equal to 0. Why? Tangent line is horizontal. Over there, f prime is, there's a local maximum. Tangent line is horizontal, f prime is 0. Over here as well. But over here, I see this is a local minimum, but I can tell there's a cusp over here, so f prime does not exist. So f can have a local minimum or local maximum, and f prime can be either 0 or does not exist. So all of this says that Fermat's theorem is telling you if f has a local max or f has a local min at C, then C is a critical number of f. So remember, at local min and local max, C is a critical number. Critical number means f prime is either C 0 or f prime of C does not exist.